Hey everyone, it's Canfield. So I have a video to accompany my linear approximations independent study. We are going to be having a quiz on this at some point in class. So here we go. So linear approximation basically says, okay, I've got some weird curve here, right? Well, if I find the tangent line of it, the tangent line and the curve have the same y value right here. So if I were just to travel a little bit along the tangent line, this is a pretty good estimation of where the actual function is. Now, as we continue out on this tangent line for a long time, it might not quite line up, but maybe it will. Anyway, linear approximation, the big idea is we find the tangent line at a specific point and we use that to then estimate something close by. And the rationale for this is sometimes functions like this are really difficult to plug numbers into, but a line is really easy to plug numbers into. So if we're trying to get close to something and we don't care about it being 100% accurate, which most scientists and engineers and that sort of thing, very, very close is good enough. So we're gonna use this sort of thing to make estimations when hard calculations are undesirable. All right, let's see. So first we got to talk about a really big idea, and that is my estimation an overestimation or an underestimation? And it all has to do with whether or not we're happy or sad. So if you think about it, if a function is concave down, which remember, that means that if we took the second derivative, so if we called this c right here, the second derivative at c would be a negative number. That's what would make a concave down. No matter where that c value, no matter where that c value is, our estimation is an overestimation. It's going to be over our actual function. And similarly, if we're looking at a concave up scenario, we have our f double prime of c. In this instance, f double prime here would need to be positive to make it concave up. And so because of that, if we think about that, no matter where we drew it, our estimation would be an underestimate. So this is true, and they like to throw this kind of stuff at us on the AP test where they're going to ask us, is this an overestimate, is this an underestimate? And it comes back to the concavity. If we can find the concavity, we're good. Whoop. All right, let's look at a non-real life application. All right. So it says for the function given below, and this is a little bit hard to see, that's okay. For the function given below, find the equation of the tangent line at x equals e. Okay, well I need to find the tangent line of f of x is equal to the natural log of x to the 8th. Okay, so I'll put my work for part A up here. I'd rather not run out of room. So f prime of x is, well, remember that the derivative of natural log is 1 over. So 1 over x to the 8th. And then remember, chain rule makes the 8x to the 7th pop out. So I'm just going to write over that 1 with an 8. So 8x to the 7th pops out. Okay, there's my wait, let's clean this up. 8x to the 7th over x to the 8th. There's no pluses or anything in here, so I can cancel the x to the 7 and 7 of those and be left with 8 over x. Pretty nice derivative. So it says find the equation of the tangent line at x equals e. So that means if I plugged in e here, that'd be 8 over e, which is, I really don't care what that is. It's a weird decimal, not important right now. But if we want to make the tangent line, so I'll need y, I don't know the y value, do I? So I'll have to leave that part out right now. But I do know this is my slope, right? My slope of the tangent line, 8 over e, x minus e. All right. And if I want to find my y value, I'll need to plug the e back in here. So y value is going to be the natural log of e to the 8th, which is equal to, remember, you can take these exponents out front. So I can say 8 natural log of e. And natural log of e, remember the question that you ask yourself when you see a natural log, you say, okay, my base, which is e to what power gets me that number I see there? And the power that we take it to the first power. So ln e is just 1. So this is just 1. So 8 times 1 is just 8. So it's y minus 8 is equal to 8 over e times x minus e. Lots of 8s, lots of e's. So part B says, use the tangent line to find the linear approximation at x equals 3, x equals 2, and x equals 10. A lot of times on the AP test, they'll say use your tangent line. Like they're saying, use that thing you just got. And so this is definitely one of those situations where if you got stuck somewhere up here and you had no idea, but okay, well, I know x is e, so you're like x minus e, I don't know the slope, so I'll just put a 3 there. I don't know how to find the y value. I'm going to put a 2 there. Okay, cool. I wrote a tangent line. It's totally wrong, but I can now use it in part B and I can plug stuff in. So just a reminder about that, a good AP tactic. Ideally, we know how to do it, but realistically, our brain falls out at some point. All right, let's see. So we're going to use our tangent line to find the linear approximation at x equals 3. So all I do now is I plug 3 in here. So y minus 8 is equal to 8 over e times 3 minus e. And I can add the 8 to both sides and say y is equal to 8 over e times 3 minus e plus 8. And you know, I can do some algebra and I can find out what that is. But linear approximation generally cares about decimals, so I'm just going to find my decimal answer here. So 8 over e times 3 minus e, bam, plus 8, 8.829. Okay, so y is equal to 8.829. And since I added the 8 and I'm able to do that each time, I'm just going to, for 2 and then for 10, well, the only difference is what x was. So 8 over e is equal to 2 minus e plus 8, and then 8 over e, 10 minus e plus 8. So in each of these situations, and remember, you know, on the TI-84, a lot of times you can just push up, hit enter on that, it'll bop it out for you. Just change the number you want. So I got 5.886, and then I need to go change it for 10. So let's say the up arrow doesn't work because some calculators, depending on the firmware on it, the software that's on the calculator that works, it doesn't have that feature. So if you push second and then, oh wait, I should show that on camera. So if you push second and then enter, it'll bring up the thing you just typed in. And if you want to do something you typed in a couple times ago, you push second and then enter, and you just keep pushing that, and it'll cycle through all the different things that you've typed in recently. Really, really useful. So now I know a lot of people are in this boat where they start typing 10 and they're like, oh, I have to retype the whole thing now. Which, like, yeah, it's not that bad, but I like to show little shortcuts. So if you go, you have this thing here and you just want to edit right here, but you need to put another character in. Your calculator says INS right there. That means insert. That is the same as this insert key on your keyboard. It actually does the same thing. The insert key on your keyboard is in the reverse mode that my calculator is in right now. So on my computer screen, if I go and I am typing, then the new character that I want to type gets inserted before the other characters that are there. On my calculator, it overwrites it, it erases it. But if I push second and then click the insert button, now it does the same thing my computer does, and I can type as many characters as I want, and it inserts them before. So the thing about the calculator, though, is it immediately reverts back as soon as you push one of the arrow keys or do anything else, basically. So I don't know why they made that decision, but that's what they did. So anyway, tangent over. So we're plugging in 10. I got 29.430. Okay. So I've got these 3 different y values. So y when it was 3, y when it was 2, and y when it was 10. Okay, when x was 2, when x was 3, and when x was 10. So C says rank our answers in order of accuracy. So if I want to think about that, I really want to think about, okay, so how far away from my tangent line's connection to the function, how far away are we? So like if we were to think about this, so our original function said the natural log of x to the 8th. And that looks like, whoa, okay. And then we care about when x is equal to e. So I'm going to go from 0 to, well, we want to look at 10 eventually. So I'll go from 0 to 11. We can go by ones. I don't quite know where my y values are going to be yet. Oh, looks like they go off the screen. So I'm going to, maybe I'll make my y values go up to 30. Let's see if that's enough. Cool, okay. So I could have picked 20. Something in my brain was like, I feel like 20 is not going to be enough. I don't know why. It was just a hunch. So it's not magic. That's what I chose. Okay. So, and then if we look at our tangent line, which I'll have to solve this for y, but that's pretty easy. X minus e. And there's just the plus 8 on the end, and so I can graph that. And if you look there, e is, if I push the trace button, and I can actually type in an x value, so e, the x value is 2.718, blah, blah, blah. So they connect each other right there. So you might notice that the farther along we go on this line, the less it looks like our real function. The farther we go to the left, the less it looks like a real function. So our actual initial f of x. So really, the closer we are to e, well, that's where we want to be. So I just look at these 3, and I go, okay, well, which one of these was the closest to e? Certainly not 10. So I'm going to go goodest and nope. So I already know that 10 is the nopest. Now I have to figure out, is 3 or is 2 better? Well, let's see. Well, e is approximately 2.7. So 3 is closer to e than 2. So 3 is better. 2 is, let's say, and that's our nopest. Okay. Wait, I said there was an whatever. Okay, so we've got our best, we've got our worst, and that's why. It's how far away is it? Now, if we look at this, we can see in our picture that any point along our tangent line is going to be above the curve. That means any of these points is going to be an overestimate. But it's not enough to just go, oh, I looked at the picture and it's above it. Usually they're going to expect some kind of reasoning beyond like, oh, I look at a picture. So what we can say is, if we were to, I'm sorry, I'm already thinking about part D. Part D says, is your answer in x equals 3 an overestimate or underestimate of f of 3, and why? So if we were to do this, well, I know f prime was equal to 8 over x. Remember that 8 over x is 8x to the negative first. If I were to find the concavity by taking the second derivative, well, we just multiply the front by 8 and get x to the negative 2. And specifically, I'm curious about when x is 3. So 4x is e. It shouldn't make a difference here. So we can say negative 8 over e squared or negative 8 over 3 squared. It doesn't matter. Take your pick. What do we see about both of these? Are they positive or are they negative? Both of these are negative. I'm not saying you should do both of these. I'm saying if you evaluate the concavity either at our original point or at the point we care about, we should see something similar. They don't throw trick questions out with this. So we can see that at the point in question, f of x, or f of 3, at f of 3, let's say at x equals 3, f of x is concave down. So S-O-U. Wow. So it's because I was about to write the word R. So our estimate is an overestimate. Okay. So, okay. On to the next one. Cool. Didn't want to run out of room. Ran out of room. If only I had, like, tons of paper. So, or planned at all before I started filming this video. Okay. All right. We'll just have Brad edit that out. Or maybe Brad too. Okay. Non-real life. Is it visible on screen? Yeah, okay. For the function given below, find the equation of the tangent line at x equals pi over 6. Okay. So we have y is equal to sine of 4x. So if we want the tangent line at pi equals, or x equals pi over 6, well, y prime is equal to cosine of 4x. Don't forget to multiply by the inside its derivative, so 4 cosine 4x. Find the equation of the tangent line at pi over 6. Okay, so let's find, when we plug in pi over 6, and we get 4 cosine 4 pi over 6. Okay, 4 over 6, you can divide a 2 out of both of them. And this is 4 cosine 2 pi over 3. So if you got your unit circle memorized, boom, super easy. Let's pretend we don't. Okay, 2 pi over 3. Well, if I'm thinking about this, it's 2/3 of the way to pi, which is here, so it's got to be over here. It's this angle, but I can draw this triangle here. And I know the 3, like 30, 60, 90 is where we see the 3s. And I know that the 30 is not 3 and 60 is not 6. I know that those switch. That's kind of how I memorized this. So this 2 pi over 3, this is going to be a 60-degree angle right here. So if it's a 60 there, then that means this is a 30. Could I have drawn this any more microscopic for you? Hold on, there. Acting like we're running out of paper or something. So that's a 60. That means this is a 30, right angle. And I want the cosine. So cosine is adjacent over hypotenuse. So I remember that the smallest angle goes with the smallest side, and 30, 60, 90 is 1, 2 square root of 3. So 1, 2 square root of 3. And also we need to take into account the direction that we went. I went to the left, so that's actually a -1. So cosine of 2 pi over 3 is -1/2. So that means this is 4 times -1/2. But seriously, if you remember your unit circle, that this is -1/2 comma root 3 over 2, like, you're already done. So, not trying to flex on you all, did that in my head before I started writing any of this. I was like, yeah, it's -1/2. I hope I don't screw it up and get a different number. So anyway, 4 times -1/2 is -2. So, the slope of my tangent line when x is pi over 6 is -2. So I can, again, we don't know our y value. Hooray! Okay, that's our m, so -2. Then we got our x minus, and what did I plug in? I plugged in pi over 6. Okay, pi over 6. All right. Okay, so now I need to find my y value. So I'll have to go back to our original and plug it in. So if we plug it in, we'll get y is equal to sine of, wait, 4 pi over 6. It's the same thing. It's going to be 2 pi over 3. Wait, hey, what? We can just use the same triangle. Opposite over hypotenuse, root 3 over 2. Bam. Done. And, okay, that's part A. B, use the tangent line. So the lights just turned out because I'm not moving enough. And throwing things didn't work. Will waving my arms work? Well, getting up, hey, all right. They make you move like 3 feet out of your chair to do it. All right, so there's my tangent line. Part B, use the tangent line to find the linear approximation at all those different... Again? They normally just make you do 1. Fine, okay. I mean, hey, I totally want you guys to do this. I think this is super valuable. All right, let's see. So we got our tangent line. All I gotta do now is plug in these x values. Pi over 5, 7 pi over 45, pi over 3. That's it. Super simple. All right. So, and I already know before we get started, well, pi over 6, pi over 5, pi over 3, these are the ones that are gonna be close. Wait, 7, having a hard time thinking about where 7 over 45 ranks on the number line. Oh, okay. Oh, right, yeah, because 7 times 6 is 42, so this is actually very close to a sixth, because 1/6 is that. So this is actually going to be our best, our closest approximation, or one that's closest to the actual function. Because remember, the farther we get away from this x value, the farther our y values are going to be. Like, so when I plug these in, the farther they are from that pi over 6, the farther off they're going to be in terms of, I mean, further off, yeah. The further off they're going to be in terms of their approximation. Okay, so use the tangent line to find a linear approximation at x equals pi over 5. Okay, well, let's just quit your complaining, Canfield. All right, so we'll do pi over 5 first. It's not that big of a deal. Why am I so depressed about it? All right. I'm literally going to use my calculator anyway. I'm filming this on a Friday. I want more coffee. I think that's what's going on. Let's see, square root of 3 over 2. All right, so I got 0.657, and then I'm just going to use my trick and go back, and because the only number I'm changing, I'm going to change to 7 pi over 45. So hard, clearly worth complaining about. So when I plug that in, I got 0.936. And then the last one I'm plugging in is pi over 3. So if I plug in pi over 3, I got negative 0.181. Okay. So I got for my different values, and I didn't talk about this in the last one. I should talk about this right now. Let's do these versus the real thing, versus y is equal to sine of 4x. So if I were doing these versus sine of 4x, and So sine of 4x, I'm going to do a little sneaky right here. I'm going to go in here so that I can type them in and then have even less work to do, which I could have done in the first place. So I got pi over 5. I got 7 pi over 45. And I got pi over 3. So so in y1 I'm going to have my original function. In y2 I'm going to just bop in my my linear approximation function, so we can compare them very easily. So we've got, make sure there's no glare. So this first one, this was our pi over 5. At pi over 5, you'll see that they're less than 0.1 away from each other, right? So there's my original, there's my estimation. That's not bad. You know, if it was money, it would be like 10 cents off. With this 7 pi over 45 or whatever that was, they're even closer. They're only about 100th off from each other. And then when we look at pi over 3, wow, we have 0.8 versus 0.1. That's a lot different. I mean, a lot when we're comparing it to the other ones. So, and that makes sense if we think about how far these are from pi over 6. This is the closest to it, a little bit farther away, a little bit farther away, and the farther away we get, the worse the approximation is. So really good approximation, pretty good approximation. Honestly, it's still fine, but nowhere near as good as our first one. Okay. And then we want to talk about over and under approximations. So if we pull our derivative back up, which was y prime is equal to 4 cosine 4x, then our y double prime is negative 16 sine of 4x. And so if we were to look through, this is a typo. We should be looking at pi over 5. So we looked at pi over 5 right here. Okay, so I actually, 4 pi over 5, oh, okay, 4 pi over 5, I know that this would be 5 pi over 5 right here. So 4 pi over 5 is going to be somewhere over here. And we're looking at negative 16 sine. So sine of 4 pi over 5, this is going to be some positive number. So negative 16 times a positive number is a negative number, which means it's concave down, which means overestimate. If it had been concave up, it'd be underestimate. Let's see how long. Okay, I've been going for almost a half hour. I don't want to rush these examples. I'm going to make a part 2. So, I mean, feel free to give them a try. There isn't really anything new except these are just applications. So we'll call this linear approximation part 1, and then I'll drop part 2 at a later point in time. So whenever you watch this, I hope you're having a great day, and I hope that your day only gets better from here. Bye!